first of a series of seminars semester. Appreciate the opportunity to be here and talking to you. Most of my professional work is actually not in this field, even though my largest project is now in space mining. Most of my professional work is in boring stuff, so I don't want to bore you with that. It's tunnel boring, grade boring, shaft boring. That's what I mostly do. But just wanted to put a plug in for those of you who don't know your little neighbor down south. It's a good neighbor. We are actually offering master and PhD degrees now in two different fields. That is really neat. First of all, as of last year, Board of Trustees of CSM approved the degrees in Space Resource Engineering. And this past fall, we got the Colorado Higher Education Commission to approve it. So we already have programs for PhD and Masters in Space Resource Engineering. And also, we're offering degrees in underground construction and tunneling. It's a fairly growing field. We are the only one in North America that offers actually a degree in this field. If anybody's interested, just drop me a note, keep in touch. I'm sure you can find us, right? And we'll talk. All right, I have a lot of slides and little time. I guess it's for 1 hour or 50 minutes or something. All right, so I apologize ahead of time because I'm going to zip through a lot of this stuff because of the volume. But being smart as you are, I'm pretty sure you can probably catch up. And before even I start, one of the icons is this field of space mining and construction. It's in this university science store. And we've had some discussions in the past and some collaboration between mines and here. And of course, Boulder has a lot of interest in this field anyway. All right, so what we'll talk about is, let's lay it out there. Why are we talking about the space mining or even construction? And what are we going to mine, where, and how? So we'll talk a little bit about time-bound and feasibility mixed into the presentation. We'll talk about lunar mining, asteroid mining, and Mars. And then I'll give you a couple of quick updates on one of the projects that I finished a few years ago on excavation part, and the drilling projects that I'm working on right now. The reason I'm going back and forth is that I don't want to be in front of the screen anyway. Okay, so space has been fascinating. I mean, we've all been somehow dazzled by it. It's interesting with a lot of the projects that I've been involved with. When we get people to come and visit our facilities, when we talk about the space, everybody goes, what? You know, it's really neat. We can talk about a lot of different technologies, but the minute you mention Moon, Mars, and space, everybody goes like, what? Even if I say somebody went to Mars and Moon and farted and came back, they want to see how it smells. I mean, it's that exciting. So we've always been fascinated to go to space and do the work. So why are we even talking about this? We know that you're bored on this planet, you want to go out and explore. And for any deep space mission, we need to do in situ resource extraction. There is no way that we can actually lift off with such a heavy payload and go up and say, okay, well, I want to have a meal. It doesn't work that way. Construction material doesn't work that way. So we actually have to go and mine it there and build our own stuff right there. Construction material, we cannot move it. God said we cannot move it on the planet Earth anyway. Construction material is typically local anyhow. So thinking about taking material up there is pretty much completely dead at the beginning. Now, it's an issue of cost, and of course, it's the issue that right now we're talking about Moon and Mars, but for deep space, at one point, the travel distance and time becomes an issue. So, what are we looking for? We're not looking for platinum or gold and all these exotic stuff. We are looking for primarily water. Even though at one point we will get involved with mining, let's say, metals, right? Oxygen, soil. But for now, the primary goal, the prime goal is oxygen and hydrogen, which comes out of water by simple hydrolysis, which is really easy to do. And most of the rocket fuels around are hydrogen and oxygen. They're room primers. So there is a lot of interest in water. So the commodity we're looking for, and it's real as a miner to even talk about it, is water. Why now? There has been a lot of renewed interest to go back to space. So the timeline when I was working on the last project was about 2015-16 to go back to Moon. Definitely missed that deadline. But now the new timeline is 25 to 26, 2025, 26, to go back. And this time we don't want to go and touch and say we did it. We want to go really do something, stay. So it's the time for going up there. And we are planning. And we are also concurrently exploring and landing on Mars. I'm sure you have followed the news. But what is even more interesting is the commercial interest in space. Up until now, it has been NASA, advanced, you name it. But now we have Blue Origin, SpaceX, a lot of billionaires are in the game, they want to do it. This tells you a lot of the story here. This is actually a slide that was presented last year in our Space Resource Roundtable at Mines, and the next one is coming in July. If you're interested, try to get in. This shows for a kilogram of water on the Earth, get it for free almost, right? But in LEO, lower Earth orbit, or the geostat, GEO, if you go there and GSO, this is the value of a kilogram of water. What does it mean? The satellite operators spend a couple $100 million to put a satellite to orbit the Earth and serve, right? They have a limited time, and of course the battery runs out. That whole 200 million or whatever is pretty much a piece of junk. They have to shoot it out in the outer space. What if you could actually refuel it, at least give it another 10 years or 15 years? This is a value proposition, right? That's why. It was really interesting and eye-opening for me that why they want to do that. So the issue right now is that if you can get a kilogram of water to the satellite in the orbit, it's worth between $3,000 to about $16,000. You want to take it from Earth? Boy, this is the cost from Earth, right? And if you take it from anywhere else, there might be an opportunity to really mine it, primarily from Moon, send it to the gateway, send it back, and it could actually be feasible to beat the price of getting that water out of the Earth. Does it make sense now? But that's why everyone is now going like, huh, it's possible. So one of my buddies have actually done the calculation. If you can get the water on the Moon, $500,000, $500 per kilo is feasible. So that's the rest of it is the cost of liftoff from the Moon and coming back to DOGO. Everybody follows that? So for us miners, we have to know how much is the value of the ore mined on site so that they can plan the rest of the operation. And that's the justification. Okay, where to mine? Of course, Moon, because we have a lot of data, not much actually sampling, and the geotech guys are going to lift the rock and play with the soil, but we don't have much of that. Nevertheless, we have got a lot of good remote sensing data. On Mars, we have water, we have methane, it's all proven, at least with remote sensing, right? There has been a lot of exploration, and of course, there are some even CO2 available in the atmosphere. Asteroids, we have done a spectroscopy, and there's a lot of goodies on the asteroids. And I didn't quite understand the asteroid till last year. We had a very in-depth discussion with one of our friends that sort of made it make sense to me. Meaning that for Mars and Moon, we have a certain distance, but the asteroids are all over the place. It's a matter of finding it, intercepting it. So it could be even closer to Earth than Moon or Mars. You go like, huh, I didn't think of it that way. Of course, asteroids are always a threat, so we keep track of it as you'll see, but mining it was a different deal. All right, Moon. What do we know about Moon? We know that we had, through a spectroscopy, we have identified hydrogen, the lunar pole. So we know hydrogen is there. The most probable way of hydrogen being there is in the water, locked down in the water. So essentially, lunar pores are cold. If there is any molecule of water, it would just get sucked into the soil, get locked. That's what we know. To quantify it, there has been a lot of studies. The best one is this one, the L-Cross experiment. So what they did, as I said, the satellites, after the lifespan is done, they shoot it into deep space. In this case, they marked a satellite, which had a little bit of a power, and actually put it in a trajectory to hit one of these craters in the lunar pole, right? And as it hits the crater, it puffed a little bit of the, earth and soil or whatever it was, and through the spectroscopy across this puff of material, they made an actual measurement. This is the number. And keep that in mind, we'll come back to this. 5.6 plus minus 2.6. Or let's say, make it simple, 6 plus minus 3. The 3, 6, 9 is typically the range that we're now looking at. So this is L-Cross, and again, it's now more definitive. So there has been a lot of discussions about going to the moon, how to mine or extract that water out of the soil. One of the ways that one of our buddies are working on at mines is actually to create a dome, heat it up, get the water out. If we can do it, great. But there are other plans as well. So again, this is about water and what we're looking for. One other thing that I thought is interesting is actually extracting that regolith or soil on the moon and making these tiles. The reason we need the tiles is that the surface of the moon is actually covered by this fine powder that is generated by impacting of the surface, right? And it's really nasty because it's sharp, very fine, and because of the gravity, when it gets off, it just floats around for a while. So these tiles that are made of the lunar regolith, or simulant of it, because we have only a few kilos of the actual material, we are using a product that has the same mineralogy, same grain size, shape, and everything. We call it simulant. So you hear the term simulant a lot in this presentation. So they actually made it with some resin so that they can actually lay it out on the ground for the lift of, of the rovers and rockets, so it doesn't splash tons of soil around or regolith. So that's one of the applications. So we'll come back to Moon later because that's the focus of the presentation. On Mars, we have done a lot of missions. This is a list of missions from the 1960s all the way to just past few weeks that we have a lander. And each one had a different mission. Again, there are maps of Mars and some of the minerals, and again, primarily we're looking for water. So that is the evidence we're looking for, and we're going to zip through. Again, this is a close-up view of the points that were higher value targets for exploration. And these are the poles, the center, forget about it, these are the Martian poles. Again, there is a good spectroscopy and analysis of what is happening there. And there are some evidences, like picture here. I mean, unless it's a stage somewhere in NASA for, tricking all of us, this is significant. I mean, what is that white stuff under the, tire or the wheel? It most likely is water, and has actually been corroborated with the spectral analysis. And again, these are the locations for high probability of having ice. And these are the pictures. I mean, look at where the regolith move out, and you see a whitish background. For most part, you're anticipating is ice. And it's very thick too. Again, you can see it in different parts. And actually, there are some features like glaciers that we have on Earth that has been monitored on the Mars surface that is actually has the signature of ice flowing right under a viscous flow regime. So you can see all of this and they corroborate. Again, a picture of the Mars, and then look at this. Again, there are a lot of evidence that somehow or other we have something like snow and ice even spreading around. Okay. And there are plans to go in, drill into the ice sheet, because we know that there is regolith and there could be an ice sheet underneath it, and extract the ice into special capsules and send it back. So these are some of the pictures and anticipated, plans. Okay, so I'm going to zip through. Another thing that has been recorded on Mars are material is called hydrates, and if you look through the hydrates, there are a few different sources and for different commodities. There are hydrates that have been spotted with ferro or iron, magnesium, carbonaceous, aluminum sulfates, and of course mixture plus ice. So there are other commodities that have been actually recorded, and there are scanning of surface in these areas to try to quantify it. All right. Next is some asteroids. It mentioned mining asteroids didn't really make much sense to me till I realized that there is a ton of them going by every day. Of course, for the most part we don't realize it, but they're there. So meaning that if we keep track of these asteroids and one of them comes to a close trajectory, there is a possibility of encountering it at a shorter distance than the other. So that opens some possibilities. The graph here is really interesting. Actually, USGS has a group that is working on this asteroid issue. Of course, for security issues, as far as a big one hits the ground, it could be like dinosaurs, right? I mean, there is not much you can do with it. And they have kept track of the asteroids based on for observation, 1980s, 90s, and so on. They started looking at the asteroids that are a kilometer plus. So then they started diverting to 140 meters plus. Then the other sizes. So this is what has been logged. We're talking about what? Then tens of thousands. So a lot of them are out there. Okay. As far as size, they're all over the place. You see, there are some special missions that has been flown out to particularly look at the asteroids. And as I said, there are some of these asteroids that are quite huge. We're talking about, who knows, maybe a few thousand tons. I mean, big size. And then the smaller ones here, as you can see, and I'm going to continue this into the next slide. You can see these are the smaller ones. So as you continue in, these are the smaller ones, the size of a football field or a couple of football fields. So the asteroids are also there. The issue with asteroid is that you cannot land on it. There was a very interesting presentation that if you approach the asteroid that's going, let's say, 20,000 kilometers per second or whatever, if you approach it and the differential speed is more than 200 millimeter per second, you keep bouncing and you bounce off of it. It sucks, right? You go for years and get approach and then bang, you're out. There is not much fuel left to chase the asteroid again. So landing on the asteroid for mining is really tricky. So some of the decisions and discussions right now is to see if they can actually go capture an asteroid, put it in a dome of some sort, and start banging on it, primarily by laser or by concentrated light that could go about to 22 to 3,000 degrees Celsius by concentrated light and laser to really start cracking it and somehow extract the material in it. This last slide is from a company called Off-World. They are one of the companies that are offering robotics for a variety of applications in space mining. So they're thinking about actually going underground on the moon, doing some mining stuff, of course, creating base and doing construction. And all of it is based on this simple module that essentially would be a robotic rover that you can fit in different tools on it. So as far as maintenance and whatnot, it works. And right now, the CEO was down there at mines last summer saying that, look, we realize that nobody's going to put the money on this unless we actually make it work on Earth. So they're trying to come up with a construction equipment that is fully automated, can do all the construction chores and mining chores with these units. All right, let's roll back to Moon. So as far as construction for the SEAL guys, there are a lot of discussions about what construction activities we need to do. Of course, we need to do a lot of digging, right? As we do here, level the ground, get it to the point that we can actually start building. Digging for trenches for utility lines, and of course we need construction materials. We have to dig to make the bricks, right? For thin rock. We have to construct a lot of launch pads for transportation, of course, and of course we have the assembly of building. And for the building assembly, now everybody is thinking about using 3D printing of the regolith to make the habitats and stuff. And actually, I'm going on a tangent on this because my take on it is that why build on surface and actually bury it where we can go down and do the tunneling if we're done. And you don't have to worry about impacts or atmospheric pressure and whatnot. Everything is down there in the tunnel. So I've put on a couple of papers that people say you're nuts, but I'll take it. I started talking about lunar tunnel boring machine. So it's in the working. You can laugh at it now, but hey, it always starts from there. For construction, there are a lot of, again, discussions, pictures floating around. The primary construction sites would be close to the poles, and primarily the South Pole, because some of the craters there in the South Pole of Moon have been identified as permanently shadowed craters. So why permanently shadowed craters is important? Because as soon as you get any sunlight, the water is gone. Because the temperature in the sunny side is around 120 to 30 degrees Celsius. The temperature in the shadow area or the poles where there is no direct sunlight is minus 150 to 160, minus. So imagine if you get any sunlight in those areas, the commodity is gone, right? So the issue is to go on the rim of these craters where you get the sunlight for energy, then operate the mining applications and all the activities down in the crater when it's permanently shadowed. There are a lot of discussions about transportation, how to go around and stuff. There are some general designs for the chariots that could go around and actually be the work. And pay attention to this because we'll come back to this later. So these are the mode of transportation. So excavation task. Why do we need to excavate? Of course, we have to get regolith for O2, and there is a process for that. So mining soil and getting oxygen out of it. HO2, water. So these are the two main priorities. Then landing pads, blast protection berms, electric cable trenches, utilities, and so on. And not only we've looked at that, there are some quantification tools. These are some artistic rendering of where a base would look like. And to me, this is a basic flaw. I mean, these cannot be a permanent base on the moon because of the impacts, right? Because of a lot of problems that we discussed. So hold on to this image. Because these are, again, artistic rendering of the launch pads and the support facilities. But for habitats, the discussions, and I'm guessing that it must have come from a single background, is to dig a trench, put a habitat there, and then cover it with soil. And as we'll discuss later, on the Earth, surface excavation makes sense because you can get this huge humongous equipment. On the moon, does it make sense? I mean, you can't get this equipment up there anyway. And if you get a truck or an excavation unit that's a few hundred ton here, on the moon you have 1/6 the gravity. So let's say if you say 500-ton truck up there, how much does it weigh on the moon? 100 tons, right? It's not as effective as you think. So going underground from get-go could actually make sense. And there are some discussions because there are something that's called lava tube on the moon that are huge. We're talking about the size of Denver lava tubes that are covered by, Earth, well, not the Earth, by the moon material. So we have some ready-made underground caverns there that we might actually tap into. Okay, so these are some of the pictures, and as far as quantities we talked about, right? So when the plan was to go back to moon in 2015, this was the timeline. So we needed to do this much excavation for different categories, for the cable trenches, landing pad, and so on. See, we needed to do a lot of excavation. So the problem is that for all of this excavation, we have to come up with a smart way of excavating it, right? And moving the earth around. And that was the question on the first project I worked on a few years ago. So for the equipment, it has to be mobile, lightweight, low power, because they don't have much power anyway. Minimum intervention by men, automatic or remote, operated. Low maintenance and again, some and fully automated. Now, difficulties. This is the catch. This is the catch. First of all, you're working vacuum. So you cannot just have your t-shirt around irrespective of temperature. Radiation. Radiation, because there is no filtering. So all of your electronic equipments, if they get exposed to that level of radiation, they are pretty much useless. So you have to have provisions for it. Extreme temperatures. I mean, where on earth we have this? Of course, it's a little funny we talk about it with this Arctic blast coming down at -30 in the U.S., but in general, we don't go beyond -50 to +40 or 45. This is the range, right? But look at the range there. It's nuts because there is no fluid to actually generalize or homogenize the temperature and balance it. Low gravity we talked about, and this is a big potential impact by meteorites. And guys, I'm not talking about a rock or a piece that's the size of a car. I'm talking about a rock that's the size of your fist, right? Or even smaller, because it comes in at 10 to 20 kilometers per hour, per second. I mean, could be pretty much any speed. That amount of energy can destroy anything. Okay. No cooling and flushing materials. I mean, nowadays you drill, you mine, you just have water to cool things up. You don't have that luxury. Dust suspension can impair the visuals. Limited source of power. The first project I was working on for space mining was back in '90s. Talking about developing a drill that could drill 1 inch diameter, let's say 10 meters, 30 feet. So in the course of discussion, I asked this NASA guy, how much power do you have, bro? Probably I can give you 10 watts. What? 10 watts? I mean, 10 watts, it's spending more energy talking about it. And that's the type of energy that they have available unless they come up with special nukes or some other forms of energy. Energy is an issue, probably. Difficulty in repair and maintenance, cost. And this cost is old, and you can probably go by about 5 times right now, about $500,000 per pound or so. And no humidity in the atmosphere. So these are the difficulties. For us, for excavation, we had to deal with other problems. See, either it's frozen soil or soil or rock, it doesn't care whether it's on the earth or on the moon. You have to break it. You have to apply a certain amount of force to break it up. And that certain amount of force predicates on having a machine that can actually support that force. On Earth, if you put the blade of your bulldozer too deep into the soil, what happens? You start just running the wheels. It doesn't move anywhere. So it requires a certain amount of mass, a certain amount of friction, right, to move the material. It doesn't mean that you're going to get a discount when you go up on the moon. So that is a major issue for excavation part. Geology, anyway, the base rock is basaltic, okay, volcanic rocks. But the surface is covered by regolith, which is powder, this fine powder. However, it gets compacted really quick. So you go to about 100 millimeter to 200 millimeter, you get to 95% compaction, meaning that it's difficult to mine. So you step on it, it's fluffy, so you start digging, hits the wall pretty soon. We have some regoliths that have been returned from the moon, and essentially we have come up with an analogous to it we call Simulant. All right. There has been some discussions and some work on the exploration. We'll come back to this later again. These are some of the different drills that have been deployed and tested here, and some of them have been deployed for application. One of the things that we have to deal with drilling on the moon, or Mars, is that there is no flushing medium. And as simple as it may sound, it's actually a damning limitation. So you cannot flush the material with air or water, so you mechanically have to move it. So all the drilling equipment that has been designed for space application work based on an auger system to move the material mechanically. And as you can imagine, it takes a lot of energy out. Okay, these are again some pictures of different drill systems, even some mechanisms for capturing the core material. For excavation, I'm sure you may have heard of, or surely have heard of the Caterpillar NASA Challenge, where every year a group of students from 12, 13 different universities go in with their robots to excavate, right? And dump the material into a bin, and they select the winner. Now, these are the ideas that have been floating around, right? A bucket wheel excavator, a chain wheel excavator, and so on. The problem, and these are some extended ideas, the problem is that, okay, all of this is fine and dandy, but none of it works in super compacted soil anyway. And for sure it doesn't work in frozen soil. And what are we trying to mine? Damn frozen soil. So, you know, it's a no-go right there. So we have to actually develop a new excavation system that can excavate compacted soil and semi-rock, if you will, right? So what do we do? What do we know about frozen soil? Because of the permafrost, right? There has been a lot of studies. And freezing has also been a part of the construction. We talk about ground freezing for some excavations, right? So we know that depending on the water content, the strength goes up and then shoots down. So when you get to the saturation point, the strength is already, you know, peaked, and then beyond saturation point, it drops. So we know this. We know that depending on the soil type, right, and temperature down below, the strength of the material goes up. But about 80 or 90% of the studies on permafrost is in this zone. Let's say 0 to minus 30, 40, 50